Hello and welcome to the UVU CS3060 Lecture 2.1, where I demonstrate how to use system calls or syscalls. So let's begin. Fair warning, what I'm about to demonstrate to you is not something you will usually do. In fact, if we start out, everybody's fairly familiar with the printf version of Hello World, where we just simply go ahead and create our little program that's going to print out Hello World. And we'll also add the extra benefit of being able to do our own little Hello World as we see fit. So, simple program here. We'll just go ahead and define ourselves a string. So char pointer str is equal to hello world. All right. If argc is greater than 1, we're going to go ahead and capture what the user asked and just simply put into our string variable argv sub 1. And then printf. We'll use the string format specifier and specify our variable. One of the simplest programs out there. Now if we make printf and run it, there's our hello world, and we can also throw other strings at it. Now, that's very simple, but we have and we understand that this is running through system calls, but I'm going to run a program called nm. nm actually shows you what the program is trying to use in the terms of symbols. Every program tries to connect to various resources using symbols. And if we nm printf, we can see there's a lot of different symbols that our program uses. Almost everything that's got an underscore or double underscore are things that you did not program specifically, but are internal. Here is our main function, right down here, and it's within the code at position 63A. There's also this put s. This is actually what printf is being translated to. This put s is able to format our output and print it out for us. This is a library call, and it's actually using the library named glibc. glibc is a very common operating system library for Linux that provides lots of services that almost every single program uses. The thing is, this is an extra layer between our function call and the actual operating system kernel system call that we want to use. So we're going to try and eliminate this. Now, what system call is actually being used by printf? Well, if I do strace is a nice little program that shows you what system calls you're actually running. You can see down here that we're using the write system call. We're writing to the number 1 file descriptor. We'll show what that is in a bit. We're writing these bytes right here, and we're writing this many bytes, 14. So just to understand a little bit better what write is doing, let's go ahead and look at the write system call. So section 2 is always the system call section. Here's write. The write function we can call it with a file descriptor, the string that we want to print, and how many bytes are included. Now this is important here because we didn't really know how many bytes were included. Printf took care of that for us. Also, please note that we have a different header this time. So let's go ahead and try this. I'm actually going to copy printf. We'll copy it to write.c. So now let's modify write. Now we're not going to use standard I/O anymore. We're going to go ahead and use unistandard. And instead of printf now, we're going to go ahead and use write. Now the first thing write needs is a file descriptor. Well, we're going to use the standard out file number. That's a file descriptor that's already defined for us. We can use that macro to conjure it up. Then we're going to print out the string, but what do we put here? We need a count. Well, let's go ahead and create a new function. And I'm going to call this, it's going to return an integer. We're going to call it count characters, count char. And it takes a string. And really simply, all this is going to do is for count equals 0, the pointer, the dereferenced pointer to string is not equal to the null character, which every string should be terminated with. And then we're going to increment count as well as string, just one character at a time. And then return count. It seems kind of funny with a for loop with no body, but everything is already taken care of inside of this for loop. If we wanted to make it a little bit more straightforward, we could do this. There, now we have a loop body. Both work just fine. So now I can go ahead and put in my call to my function. And we'll call count char of string. And that should print out, that should call the system call with the file descriptor, my string of bytes, and the number of bytes that I want printed out. Now I do want to do one other write. I like my carriage returns. So we're going to go ahead and print out a new line and one of those. We write this, make write, and we run it. And there's hello world, and there's my test string. Now let's take a look at what system calls we're actually making. If we use strace on write, again, just like we expected, write is writing to file descriptor 1, hello world, and there's the 13 bytes that we tell it to. And here's the 1 byte we told it to there. So let's take a look at the symbols that are being used. Well, here's the deal. The write function that we use is actually still a library function of glibc. Again, we are not using a system call directly. We are actually using a library function through glibc to get to the write system call. Well, let's see if we can do a little bit better. I'm going to copy write. Actually, before I do that, there's actually a syscall a function, part of unistandard. It has syscall.age, and what we can do is send it the actual number of the system call with all the parameters for that system call. And we know what the 3 parameters are for the write system call. So let's try and use this. We're going to go ahead and add this include header, and now try syscall and see if that makes a difference. So I'm going to copy write.c. Let's copy it to syscall.c. All right. We're going to go ahead and include syscall.h. But instead of write, we're going to simply going to change this to syscall. But this time, we're going to specify the system call we want to use. Now, syswrite is actually just a macro that is defined in the syscall.h. You're always welcome to go take a look at that header to find out more about the different system calls that you can execute. All right, so simple change. Now we're calling the syscall function. I'm going to make syscall and run it. Make sure it works. Hello world, and there's my test. Now if I do strace, it should do exactly what I expect it to do. And there you can see I'm making these system calls, the right system call, and it's doing what I expect. All right, let's take a look at the symbols. So we look down here, and yet again, syscall is even a library function of this glibc. As you can see, glibc is pervasive in so many ways. What glibc is doing here is it's going through the effort to arrange the registers just right so that the system call can happen. So, if we want to call a system call directly, we're going to have to go one level deeper. We're actually have to try and eliminate this glibc altogether. So I'm going to copy syscall.c, and I'm going to copy it to raw syscall.c. Now, there's a good chance I'm going to make a few errors when I do this, but bear with me. So what I'm going to do is I'm going to replace these syscalls with just a function. Let's go ahead and call that function syscall write. And all we're going to do is send our string to it and syscall write a new line. There. So I'm going to create a new function. I'm doing this because there's a lot of work involved with making a raw syscall. This function is going to return an integer. It's going to be called syscall write, and it's going to take a simple character variable, character string. Now I'm going to have to define a few variables here, simply because of the way I'm going to make this raw system call. And they're going to be longs. We're working in a 64-bit environment, so we have to do this. We, of course, have the syscall number. Actually, we don't need the syscall number. What we need is the output file descriptor, which was standard out file num. We need the count, char count is equal to count char. How's that for confusing? And then last but not least, I'm going to create a retval variable so I can return something. And we'll just simply return retval here. Now, in order to do this, I have to write assembly code. So I have to use the ASM, and because there are side effects, I have to use volatile. So the assembly has two sections. It has the actual code. All right, we'll put that in there. It has the input, or I mean the output. Starts with the output, and so we're going to call this ret. It's going to be a written register, and it's going to contain retval. All right, so that's the output, the input for this is going to be our variables. So we're going to say FD is a register represented by output FD. Our string is going to be a register that's represented by stir. And finally, our count is going to be a register represented by char count. Whew. Finally, it's important that we specify the registers that are going to be clobbered here. There are actually a number of registers I'm going to work with. Let's just put all of these in here. RSI. Now these are registers I'm going to use to make the system call. So I have to specify that they're going to be used. So let's go ahead and write the assembly code for this. So I'm going to first start by moving 1. And 1 is our actual system call. I'm not going to go, there's actual numbers assigned to each, and we'll call this move Q, to each system call, and so I'm using just the number 1 to represent the right system call. I'm then going to send to, let's see, we're going to go ahead and send our file descriptor to the first necessary register, which is RDI. And then we're going to send our string into RSI. And then we're also going to move our count, wrong way bracket, our count into RDX. Now, how do I know which registers I need to copy these into? Well, there are, the Linux operating system defines what these registers are, and you can find documentation in the Linux source code on how this works. Now I can do syscall. And finally, I want to take the result, so RAX, and store it into RET. That's a lot of code there just for one particular syscall. But what I'm doing is setting up the registers that are necessary for the system call and then performing the system call operation. Now there's this concept of portability. What I've done here will only work on 64-bit Intel hardware. It won't work anywhere else. 32-bit Intel hardware, I'm using the wrong registers. The ARM architecture, syscall is not what I would use. There's all sorts of things that make this particular bit of code unusable on other architectures. All right, now the real trick. Let's see if this actually builds. Oh, I haven't finished. Yeah, I did syscall right. So I'm going to go ahead and delete these lines. I don't need them anymore. We'll save it. And we will make raw syscall. Ooh, not good. What did I do wrong here? Oh, reval is undeclared. How about that? So I've got to go to line 29. There we go. This should be red val. And I really should end my code with a semicolon. If that was the only error I had in this code, it's a miracle. Here we go. So, invalid ASM, operand. Let's find out why that's doing what it's doing. So likely the problem I have here is the fact that these registers need to have double percent signs in front of them. A common mistake. So let's go ahead and write this and save it. Let's see if we make it now. We do. So let's run it, raw syscall, and there it is. Both cases work. So we use strace again to try this out. And you can see, just like we expect, it's using the right system call. We told it to. But now, if we take a look at the symbols for our raw syscall, now the only glibc functions we have is this start main, which always happens, and also this finalize, which comes at the end. But notice there is no library call made here. We are calling the system call directly to the operating system and handling it. And we're doing that the hard way. We're actually generating our own assembly code to perform the system call. Now, which way is easier? Clearly, you're going to want to use library calls to avoid this. Library calls are put there for your convenience. And there's no shame in using library calls. But realize that if you need to make a raw system call, it is possible to be done in C code. And this is probably the best way to do it, although there are other ways. Thank you very much. I appreciate your time, and good luck.